We'll come to an example on how to find the surface area of a parametric surface. In this question, we're asked to find the area of the surface of the cone with the vector equation shown here, r of u comma v, where u is on the closed interval from 0 to 2, and v is on the closed interval from 0 to 2 pi. So our goal is to find the surface area of this cone here. Given a smooth surface given by r of u comma v, the surface area is equal to the double integral over the surface S integrated with respect to S, which is equal to the double integral over the region R, where the region R would be in the UV plane, of the magnitude of the partial derivative of R with respect to U crossed with the partial derivative of R with respect to V differential A, where again R is the region in the UV plane, and therefore differential A is equal to du dv or dv du. So going back to our example, looking at this surface integral, S is the surface of the cone. Looking at this double integral here, which we'll use to find the surface area, R would be the projection of the cone onto the UV plane, this yellow circle here, where if we look at just the UV plane, it would be this circle here, centered at the origin, with a radius of 2. So to find the surface area, we'll first find the partial derivatives, then the cross product, then the magnitude, and then finally set up this double integral. So to find the partial with respect to u, we differentiate each component of r with respect to u. So the partial derivative of u cosine v with respect to u would be cosine v. The partial derivative of u sine v with respect to u would be sine v. And the partial derivative of u with respect to u would be 1. And now to find the partial with respect to v, we differentiate each component with respect to v. So the derivative of u cosine v with respect to v would be u times negative sine v, or negative u sine v. For the y component, we'd have the derivative of u sine v with respect to v, which would be u times cosine v. And for the z component, we'd have the derivative of u with respect to v, which would be 0. Now for the next step, we'll find the cross product, and I've already set this up and done some of the work to save some time. This cross product would be equal to this 3 by 3 determinant, where the first row of the unit vectors I, j, and k, the second row of the components of the partial with respect to u, the third row of the components of the partial with respect to v. Using the expansion by minors method would give us this line here, where to find this first 2 by 2 determinant, we eliminate the row and column of the I vector, which is the first row and first column. Notice how the remaining elements are the elements in this 2 by 2 determinant. For the next 2 by 2 determinant, we eliminate the row and column of the j vector, which is row 1, column 2. Notice how we do have a minus here in front of the second 2 by 2 determinant. The remaining elements are these elements here. And then finally, for the last 2 by 2 determinant, we eliminate the row and column of the k vector, which is row 1 and column 3. These 4 elements make up this 2 by 2 determinant. And now to evaluate the 2 by 2 determinants, we need to find this product minus this product for each 2 by 2 determinant. So cosine v times 0 minus 1 times u cosine v gives us negative u cosine v times I. And then we have minus cosine v times 0 minus 1 times negative u sine v, which becomes positive u sine v, but because we have the minus here, we end up with minus u sine vj. And then for this 2 by 2 determinant, we have cosine v times u cosine v minus sine times negative u sine v, which gives us u cosine squared v plus u sine squared v. And notice how here, if we factor out u, we get u times the quantity cosine squared v plus sine squared v, which is just u times 1. So in component form, notice how the z component is just u. Let's go back to our first slide and write down the cross product. So now we know the cross product has an x component of negative u cosine v a y component of negative u sine v, and a z component of u. So the next step is to find the magnitude of the cross product, which again I've already done some of the work here. The magnitude of the cross product is equal to the square root of this sum here. Simplifying the exponents, we get the square root of u squared cosine squared v plus u squared sine squared v plus u squared. And if we factor out u squared from these first two terms, again notice how here we have cosine squared v plus sine squared v, which equals 1. And therefore we have the magnitude of the cross product is equal to the square root of just u squared plus u squared, which equals 2u squared, which would be equal to u square root 2, or square root 2 times u. Remember, u is on the closed interval from 0 to 2, so we know u is positive. So again, going back to the first slide, we now know the magnitude of this cross product is equal to u times square root 2, or if we want, square root 2u. So now going back to our formula, we know the surface area is equal to the double integral over the surface S integrated with respect to S, which is equal to the double integral over the region R, which again, this is the region R, of the magnitude of the cross product, which we know is, let's write it as square root 2u, and let's use the order of integration du dv, where the limits of integration for u are from 0 to 2, and limits of integration for v are from 0 to 2 pi. Now let's evaluate this to determine the surface area. Let's go ahead and factor out the square root 2 and write this as the square root of 2 times the double integral. So the antiderivative with respect to u is going to be u squared divided by 2. And now we need to find big F of b minus big F of a. So when u is 2, we have 2 squared divided by 2. When u is 0, we have 0 squared divided by 2. This simplifies to just 2 minus 0, which is 2. Let's write this as 2 square root 2 times the integral from 0 to 2 pi dv. Well, the antiderivative of 1 with respect to v would just be v. So we have 2 square root 2. The antiderivative is v. Evaluating here, we have 2 square root 2 times, this would just be 2 pi minus 0, which gives us 4 pi square root 2 as the surface area of the given cone. I hope you found this helpful.